Chapter 4, Part 4, Naming Alkenes and Cycloalkenes. Also, Physical Properties of Alkanes. How to name alkenes and cycloalkenes. First, choose the longest chain containing the alkene. This is the parent chain. So this is another situation where the alkene is more important than the substituents, and so you want to find the longest chain that contains the alkene, even if it is not the longest chain overall. Replace the ane suffix with ene. And numbering the chain must go across the double bond. Give the alkene the lowest number possible. Include the locations of the substituents. Okay, so let's look at these examples. Go ahead and pause and just take a whack at it, see what you can do with it. Okay, so in this first example, it's pretty clear where we need to start numbering. 1, 2, 3, 4. And I want to define what it means to go across the double bond. So that just means that whatever your number is, your next number needs to be on the other side of the alkene. So, for example, let's say this one over here, you couldn't number 1, 2, 3. You would have to number through the alkene. Not that that 1, 2, 3 was going to be the longest chain anyway, but the numbering has to go across. So, okay, back to our first example. It's a 4-carbon alkene, and the alkene starts on carbon number 1. So this would be called 1-butene. In our next example, we have 5 carbons, and the alkene is closest to the right-hand side. So we're going to number 1, 2, 3, 4, 5. So this molecule is called 2-pentene. Okay, our next example, the alkene is in the same place no matter which way you start from, but you have to start from the left-hand side because we also have this methyl group. So 1, 2, 3, 4. So this is going to be 2-methyl 2-butene. Now, I also want to go ahead and mention, even though we're not going to throw this into our naming yet, that your sp2 carbons here, their configuration is locked, unlike your sp3 carbons, which have free rotation around the bonds. And so there are actually 2 different forms of 2-pentene. The form that is pictured is what's called trans 2-pentene, and we could also have cis 2-pentene. And right now, we're not going to worry about that, but I wanted to let you know that that is a thing. Also, note that the 2 can be put in front of the ene within the name, so 2-methyl but 2-ene. This is important for when you're naming things that have many substituents or functional groups. So alkenes that also contain hydroxyl groups, that's when you're going to start wanting to put the numbers within the name. Okay, last example. The alkene is down on this end of the molecule, so we want to start numbering from the left. So we have 2-methyl and 5-methyl. So those are the same functional group. We're going to have to say 2,5-dimethyl and then 2-hexene. And then we also have some compounds that are alkenes, and you can put the IUPAC name, but all of these also have common names that you hear pretty frequently. So the first molecule is the IUPAC name is ethene, but its common name is ethylene. And you've probably heard that in reference to the polymer polyethylene, or PET. It's a really common plastic. Propene, propylene. You've probably also heard about polypropylene. And then 2-methylpropene is isobutylene. I also want to point out that none of these alkenes have numbers indicating where the alkene starts, and that's because no matter which way you put the double bond, it's still going to be on number 1 because there's only 3 carbons. So you don't have to include a number if there are not other options for where that alkene could be. So let's name cycloalkenes. First, we're going to go through the rules and then we'll apply them in practice. In cycloalkenes, give the carbon atoms of the alkene the 1 and 2 positions. Give the substituents the lowest numbers possible at the first point of difference. I'll clarify what this means when we look at the practice problems. In cycloalkenes, do not give the number of the double bond since it is always 1. In cyclic polyenes, meaning you have multiple double bonds, the number does matter. You're still going to give alcohols priority. So if you have a cycloalkene and it also has an alcohol, the alkene is no longer number 1. The alcohol is, unless they start on the same carbon. Okay, let's look at our practice problems here. First, I want to define what some of these things meant. So the lowest numbers possible at the first point of difference. So the point of difference is just referring to, let's use this example real fast. If the alkene is automatically numbers 1 and 2, you have 1, 2, or 1, 2. Those are 2 different options. So the question is, at which point in the ring do I see something different? So if I go clockwise, I get to the methyl group just 1 carbon after the alkene. If I go counterclockwise, I don't get to the methyl group until 2 carbons after the alkene. So the point of difference is where the ring becomes different. So we want to go clockwise for this one. So that's the numbering scheme. Go ahead and pause and give yourself a second to try to name these compounds, and then we'll talk about it. Okay, so in the first one, we have an alkene, and we also have a methyl group on the alkene. So that should be carbon number 1 because it's also a substituent. So this would be 1-methyl, 1-cyclopentene. The most common mistakes that students make in naming these types of compounds is, first of all, when you're naming an alkene, students often forget to swap out the AN infix that we're used to using for the EN infix. And then students also really commonly forget to put cyclo in. So always make sure that when you come up with an IUPAC name, that it truly does explain the compound that you're looking at. Okay, in our next one, we have a methyl on 3 and we have a methyl on 5. So this is going to be 3,5-dimethyl cyclohexene. And now notice we haven't given any numbers to the alkenes, and that's because the alkene is automatically number 1, and so we don't have to say it. Now on our next molecule, the alkene is not automatically number 1 because we have an alcohol present. That is going to be number 1. So the question is, do we want to number clockwise or counterclockwise? We're looking at this. If we go clockwise, we hit the first substituent and the alkene much faster. So we want to go clockwise. So what would be the name of this molecule? You have 2-methyl cyclohexenol, or 2-cyclohexene-1-ol. Whoops. On this next one, cover up the name briefly. We have an alcohol and we have an alkene. So we're going to number from right to left so that the alcohol gets the highest priority. So this molecule has a methyl group on the 4th carbon. So we should come up with 4-methyl, 3-pentene, 2-ol. So this is a really good example of when putting the number in the name, it makes more sense, because if you tried to put 3,2-pentenol, it would be unclear which numbers go with which feature, because right now the 3 clearly goes with the ene and 2 clearly goes with the ol. Okay, let's take a look at some common alkene substituents. So first we have what's called vinyl. And so this is just when the sp2 carbon of the alkene is directly attached to whatever it is substituting. And the other one is allyl. So this is where you have the alkene separated from your main compound by a CH2 group, an sp3 hybridized CH2. So for example, the first molecule on the left could be called bromoethene, or you could call it vinyl bromide. The next one could be 3-chloropropene or allyl chloride. The next compound could be called Ethenol Cyclopropane. So notice this is like an ethyl group, but I added in the En infix to show that it has a double bond. So ethenol cyclopropane, or you call it vinyl cyclopropane. And on our next one, we have an alcohol. We have to number around our ring. And then we have the allyl group. So the simplest name would be 3-allyl cyclohexanol, or you could call it 3-prop-2-ene-1-yl cyclohexane 1-ol. So that's a lot going on. This is the easier name for sure. Okay, let's talk about how to name alkynes. It's very simple, and the rules are almost identical to the rules for alkenes. So again, you're going to number in a way that gives the alkyne the lowest possible number. So this first compound has the alkyne starting on carbon number 2, and there's 5 total carbons. So we know that the family name is pentyne, and it should be 2-pentyne. And the most common mistake that students make with naming alkynes is just losing carbons within the alkyne. So make sure that you remember that there's a carbon at the start of that triple bond and at the end, and that the triple bond is not showing a triple bond between these 2 carbons. Okay, on the next one, we have an alkyne and an alkene together. And this is kind of an interesting rule. The alkene comes first based on the alphabet. So 1, 2, 3, 4, 5. So this is 1-pentene 4-ine or pent-1-ene 4-ine. In our next molecule, we have a chlorine, and this is a 4-carbon alkyne. So we're going to start numbering up here because it's closest to the chlorine, since numbering this way or this way wouldn't change the actual name of the alkyne itself. So we're going to choose our direction based on the chlorine. So this is 1-chloro 2-butyne. Now in our next 2 molecules, we also have alcohols. And remember, the alcohol is the priority still. So this is 3-butyne 1-ol. In our next molecule, we have the alcohol over here. Make sure that you are counting the longest carbon chain. So it's going to start at one of these methyl groups. You can pick either one. Two-methyl, 4-pentyne, 2-ol. Okay, the last thing that I want to talk about in this video is the physical properties of alkanes. Remember that for the nonpolar alkanes, the major intermolecular force is London dispersion forces, and so that's going to be dependent on the molecular weight. So as the number of carbon atoms increases, so does the boiling point and the melting point. That's what this chart is showing you. Also, the shape of the alkane matters. So all of these compounds here have the formula C6H14. They're all isomers of hexane, but look at how different the boiling points are. And this is all based on shape. So just plain, linear, normal, unbranched hexane is going to have the highest boiling point because it has the most surface area and the most entanglement with other hexane molecules. But as you start substituting the hexane and it starts to take on a more spherical shape, you're decreasing the surface area and therefore decreasing the London dispersion forces. And so your boiling point is going to become lower because you don't have to overcome as much of an energy barrier to boil these compounds.